diamagnetic anisotropy. The chemical shift of protons that are attached to sp2 carbons are going to appear normally at a higher frequency than what we would normally predict. For example, let's take this benzene molecule. So this is our sp2 carbon, and these hydrogens are going to come somewhere between 6.5 and 8 ppm, right? And whereas if you take the alkene, these hydrogens which are connected to the sp2 carbons, they are going to come somewhere between 4.7 and 5.3 ppm. And similarly, the hydrogen in an aldehyde which is connected to the sp2 carbon is going to come somewhere between 9 and 10 ppm. Now, these unusual chemical shifts are due to an important phenomenon called as diamagnetic anisotropy. When you say anisotropy, it means different in different directions. Now, what is this diamagnetic anisotropy and how this is going to affect the chemical shift of the protons in compounds which have pi electrons? Now, let's do this with an example. Let's take the benzene molecule. We know that the pi electrons are less tightly held than the sigma electrons, and therefore they are free to move when an external magnetic field is applied. Let's say you're going to apply an external magnetic field to a compound which has pi electrons. Now, the pi electrons are going to move in a circular path, creating a local magnetic field. Now, what is more important here is the direction of this local magnetic field in the place where this hydrogen is present. Here in this case, the local magnetic field is exactly in the same direction as of the applied magnetic field, which means the local magnetic field is reinforcing the applied magnetic field. Let's go back to our equation for finding the effective magnetic field that the nucleus is going to experience. B effective is equivalent to B applied minus whatever the effect the local magnetic field is going to bring it. Here, the local magnetic field is reinforcing the effect of the applied magnetic field. So the actual magnetic field that the proton is going to experience is definitely going to be more, because this is going to be a very, very large number. And therefore, these hydrogens are said to be de-shielded and are going to definitely take a higher energy to come into resonance, and therefore they will show signals at a higher frequency. And the same thing happens even in alkenes and aldehydes. As you can see from here, here are your pi electrons, and they are going to generate a local magnetic field. And obviously, you can see the direction of the local magnetic field where the two hydrogens are present is exactly in the same direction as that of the applied magnetic field, reinforcing each other. And therefore, they are going to be de-shielded, right? And they are going to provide signals somewhere between 4.7 to 5.3 ppm. In the same way, the aldehyde protons are going to also be in the de-shielded region, right? Showing signals between 9 and 10 ppm. On the other hand, when you consider an alkyne molecule, this hydrogen that is connected to an sp carbon is said to be appearing at a lower frequency region. So this proton is going to come somewhere around 1.9 ppm. Now, what is the reason why this hydrogen is showing a peak at a lower frequency region, or why this is shielded, why this proton is shielded? Now, again, the reason is diamagnetic anisotropy. Now, let's take a look into this alkyne molecule. We know that in alkynes, there are going to be 3 bonds, and out of the 3 bonds, one is going to be a sigma bond, and the other 2 bonds are going to be pi bonds. And now, because of these pi bonds, there is going to be a local magnetic field that will be generated because of the circulation of the electrons, circulation of the pi electrons. Now, when you take a look into the direction of this local magnetic field that is generated by the pi electrons in the position where this hydrogen is present, you can see that it is in the opposite direction with respect to the applied magnetic field. So you can tell that some of the applied magnetic field has been cancelled by this local magnetic field. So here the B effective is going to be a smaller number, right? So B applied minus B effective, because the B local is going to definitely cancel some of the effects of the applied magnetic field, making the B effective a smaller number, and therefore it only needs a smaller amount of energy to come into resonance, or it shows a signal at lower frequency region. So it is because of diamagnetic anisotropy that different protons experience different magnetic fields, and therefore they show up at different frequencies in the NMR spectrum.